class. In this video, we're going to be looking at ionic bonds. The learning intention of this video is for us to understand the composition of an ionic compound, to explore the differences between monatomic as well as polyatomic ions, to develop an understanding of ionic bonding, and to use the Bohr model as well as the Lewis dot diagram to represent electron transfer processes. So the first thing that I'll be talking about is what is an ionic compound. So an ionic compound, also referred to as a salt, is essentially a substance that is made up of ions. More specifically, an ionic compound is a compound that is made up of both cations as well as anions. So you should already be familiar with what cations and anions are. So cations and anions, they are just charged particles. And to make these charged particles, you either lose electrons or you either gain electrons, as shown by this diagram over here. So a cation is an ion that is formed by losing electrons, and because you're losing electrons, this makes a positively charged ion, whereas an anion is a charged particle that had gained an extra electron, and because you gain an electron, which is a negative charge, that's why it's going to have a net negative charge overall. So we now know that the composition of an ionic compound consists of a cation as well as an anion. However, the cations and anions that make up an ionic compound can be further classified as a monatomic ion or a polyatomic ion, okay? So you can actually tell what the kind of definitions are going to be based on the prefixes as well as the examples shown on this Venn diagram. So look at the prefix mon and poly as well as these examples over here. Can you guys come up with a definition of what monoatomic ions are as well as polyatomic ions? If you guys have guessed this correctly, you would understand that the prefix mono means one, so therefore monoatomic ions are essentially ions that consist of one singular atom. This is all shown on the examples on the right hand side in the table, and these are the common examples that you will encounter as you learn in this subject, okay? One thing I'd like to add is that this is not spelt as monoatomic, so you actually remove the O from the word mono, okay? So it's just monatomic ions. One thing I also want to point out in this particular table over here is that they've divided the cations, or pretty much the metals, on the top half of the table, and all the non-metals or all the anions on the bottom half of the table, okay? Notice that in terms of the naming for the metal ions, they actually remain the same as the names shown in the periodic table. The only difference is that for the non-metal component, the actual name changes. In particular, the actual suffix changes. So in this case, instead of having an "ine" at the end, they've actually changed that to an "ide." And we're going to go into a bit more detail later on as to how we actually name these monoatomic ions. In contrast, poly means many, so therefore polyatomic ions essentially means it's an ion that consists of more than one atom, okay? And as shown on the right hand side, there are many different types of polyatomic ions. Unlike monoatomic ions, which the naming is a bit more easier and you can kind of find what the naming is based on the periodic table, each of these polyatomic ions have their own actual special names, so therefore you have to actually rote learn these names for these polyatomic ions. However, the good thing is that you don't actually need to know all these polyatomic ions. I personally don't even remember all of the polyatomic ions shown on this particular list over here, but as I said, as you do more chemistry and as you continue studying, you will encounter more and you'll start to memorize this without knowing. On this particular slide over here, I'm showing you some examples of ionic compounds. So I'll show you one for sodium chloride, sodium fluoride, as well as ammonium nitrate. And if we actually zoom in, we can actually see that these ionic compounds do consist of charged particles, a cation as well as an anion. So you can see it by these charges over here. As you can see on this slide, I have 6 examples of ionic compounds, and there are 2 things that I want to show you using this example. The first thing that I want to show you is that for any compound that consists of at least one metal element and at least one non-metal element, those compounds can be readily identified as an ionic compound, okay? So what I've actually done is I've actually color coordinated all the metals in red, and all the non-metals in blue. So I've got 4 examples over here that contains at least one metal and at least one non-metal. So for these compounds over here, I could readily say that is for sure 100% an ionic compound. However, notice that I've got 2 examples from the 6 that only consist of non-metals. Now, most students often think that because this only contains non-metals, this is not considered to be an ionic compound. Instead, they might say, okay, because it's non-metals, it will therefore have a covalent bond. So therefore, this is going to be a molecular compound or a covalent compound, okay? However, you can actually still have examples. So you still have molecules that are still considered to be ionic compounds as well. So they don't actually have covalent bonds, but instead they have an ionic bond. At the moment, it's going to be ridiculously hard for you guys to identify whether a molecule is considered to be ionic or covalent. But as you guys actually study more and gain a bit more knowledge afterwards and be familiar with more molecules, you will start to recognize which molecule is considered to be ionic and which one's going to be covalent. But for the purposes of the subject, don't really worry about it all. Just don't fall for the trap that you think that all non-metal compounds are strictly covalent. Another key detail that I like to point out is that all ionic compounds are electronically neutral. So what that essentially means is that their overall charge is 0. And the reason why that is because the composition of the ionic compound, so meaning the cations and anions, the number of cations and anions are in a certain ratio that allows for these charges to therefore cancel each other out. And I'm going to use these 2 examples down below to show you what I mean by this. So for calcium chloride, there is 1 calcium ion to 2 chlorine atoms, okay? And we know that calcium is going to have a positive 2 charge because it has 2 valence electrons and it wants to become stable by losing 2 electrons. On the other hand, chlorine has 7 valence electrons and needs 1 extra electron to be stable, so therefore it will gain an electron and have a net charge of -1. We can clearly see that the ratio of positive charges is +2 to -2, so therefore these cancel each other out. And for the next example, sulfuric acid, hydrogen will have a +1 charge, whereas the sulfate ion has a -2 charge. And you can kind of see that each of these oxygen atoms over here carries an a negative charge each, so therefore -2 overall. So therefore +2, -2, and as a result they neutralize each other, hence the overall charge of the ionic compound is 0. Now it's really useful to know that the overall net charge is 0, is because that when you later learn how do you actually come up with the ionic formula, this is going to help you see whether the formula that you've obtained is the correct answer by seeing whether the amount of positive charges balances the number of negative charges, okay? So for instance, let's just say that your formula was H3SO4. This would imply that you've got more positive charge than negative charge, so therefore that would imply that your formula is actually incorrect. And as I said, we will learn this in future lessons. The next part of the lesson is understanding how do ionic compounds form. Now, the reason why ionic compounds form kind of goes back to this page over here again, which is related to electronic stability. So the reason why ions are formed, the reason why ionic compounds are formed is so that the individual atoms can actually achieve electronic stability by gaining a full valence shell, right? So in the case of ionic compounds, they are formed when 2 singular, meaning 2 monatomic, or 2 groups of atoms, meaning 2 polyatomic atoms, actually are transferring and exchanging electrons between each other, okay? So essentially, you're going to have one substance that's going to be an electron donor, whereas another substance is going to be an electron acceptor. And that's kind of depicted by these examples down over here. So in this example down below, it's a cartoon representation, but you've got one donor, okay? And you've got one acceptor. As you can see over here on the left hand side, both of them are quite unhappy, right? So in order for them to be happy, for them to become stable, what happens is that a donor, Emily, gives up her blanket to Sarah, and after doing so, notice that both of these substances, or both of these humans over here, are actually quite happy now. Similarly, on the right hand side of here, you've got sodium and chlorine on the right hand side. Sodium doesn't need the extra electron, whereas chlorine does. So sodium transfers its electrons to chlorine, and in doing so, both of them are now quite happy, right? So the ions in an ionic compound are held together by ionic bonds. So what that is saying is that the cations and the anions in the compound, they are attracted and held tight to each other by a force of attraction referred to as ionic bond. Now this force of attraction isn't a physical link at all. It's just like a imaginary link that is due to the electrostatic forces of attraction between the cation, positive charge, and the anion, and this occurs because of this electron transfer process. In contrast, molecular or covalent compounds are formed when two nonmetals share electrons together, okay? So make sure that you understand the differences between an ionic bond versus a covalent bond. As you can see over here, a covalent bond occurs when you're actually sharing electrons. So notice that Emily and Sarah are sharing the blanket. And for the molecule oxygen, they're sharing, each oxygen atom is actually sharing 2 electrons each. In total, 4 electrons are being shared amongst them. Let's now have a go to see whether we can answer the following checking for understanding questions. There's about 5 multiple choice questions, so give yourself 5 minutes in total. The first question reads, ionic bonds consist of the something of valence electrons. For ionic bonds, you guys should actually understand that this occurs by transferring or exchanging electrons from one party or from one substance to another. So therefore, B is going to be the correct answer. This question reads, an ionic bond is the attraction between what? The correct answer should be oppositely charged ions, so essentially between a cation as well as an anion. The third question reads, which of the following is not a step in forming an ionic bond? So let's read this. It says, one atom shares its electrons with another. Automatically by the word shares, that indicates that's covalent, so therefore that is going to be the correct answer. That is not a feature of ionic bonding at all. The next question reads, why do ionic bonds form? So in this case, we know that ionic bonds form because they want to achieve electronic stability. So therefore, in this case over here, the correct answer should therefore be B. The next question is, which of the following is not an example of polyatomic ions? So poly means an ion, a charged particle that consists of more than 2 atoms. So therefore, the C is going to be the correct answer because C is an example of a monatomic, just an ion consisting of one singular atom. We are now moving to the last part of today's lesson, where we're going to be looking at drawing the electron transfer diagrams to represent how ionic compounds are actually formed. So there are 2 ways for us to actually illustrate the electron transfer mechanisms for ionic compounds to actually form, okay? One of the ways is by actually drawing the Bohr diagram. And in doing this method, what you need to do is that you will need to actually draw the individual Bohr diagram for each element to show this process. And I want to be showing you an animation to help you guys visualize this process. So if I had sodium and fluorine, you would need to draw the Bohr diagram, so therefore show all electrons for each individual element. Once you've done this, what you need to do next is you need to actually draw an arrow to show the movement of the electrons. Because sodium has 1 valence electrons to give away to become stable, it will give it to fluorine, which only requires that extra electron. So once you've done that, all you really need to do, other than showing the electron transfer arrow, is that you would actually need to show the individual charges. So therefore, the charges of sodium and fluorine following this process. Another way of doing this is by doing this using the electron dot diagram, also referred to as the Lewis dot diagram, okay? And in this particular method, this is a more simpler way and a more efficient way of doing this process because you only need to show the valence electrons. So in this example of here, we know that calcium has 2 valence electrons because it's found in group 2. Chlorine, on the other hand, is found in group 7 and it's got 7 valence electrons. Because chlorine only needs 1 valence electron in order for it to become stable, each chlorine atom will pick up 1 valence electrons from calcium, and in doing so, each of these atoms will therefore become stable and they're happy. And once you've done that, again, afterwards, you actually just need to show the individual charges because it now has either gained or lost an electron. So again, just to re-emphasize, I've got two different examples over here, one showing the Bohr diagram and one showing the Lewis dot diagram. Again, same process applies. Metals donate their valence electrons, so you always start the diagram from the metal or from the one that's going to be giving away the electron, and the end of the arrow is where the electron acceptor receives the electron. So they're generally going to be the anion or the non-metal in this case over here. So that's just one thing that I wanted to point out. When you're actually drawing these electron dot diagrams or the Bohr diagrams to show the electron transfer mechanism, make sure again that you are including the actual charges, because we know that if you gain or lose an electron, this changes the balance between protons and electrons. Hence, it will either have an overall positive charge or an overall negative charge. And that's shown over here in these examples. So therefore, make sure you're also doing the exact same thing as well, because generally this is an area that most students often forget. I'm now going to be going over 4 examples in total. I'm going to show you 2 examples of how you would actually do this using the Bohr model, and another 2 examples of how you would do this using the Lewis dot diagram. So for the very first example, lithium and fluorine, I need to draw the Bohr model of each individual element. So for lithium, lithium has an atomic number of 3. It's found in group 1. So therefore, it's going to have 1 valence electrons, 3 electrons in total. Fluorine, on the other hand, has atomic number of 9. It's found in group 7 or group 17. So it's got 7 valence electrons, okay? So if you were to draw the Bohr model of fluorine, it's going to look something similar to this. We know that lithium wants to lose that valence electron, and we know that fluorine needs only 1 extra electron in order for it to have a full outer shell. So for this very easy example over here, all you really need to do is move that electron over to fluorine. So you would need to therefore draw an arrow to show the movement. And you, again, just to emphasize, you move it from the cation or the electron donor to the electron acceptor. In doing so, therefore, lithium will now have a net charge of +1, and I've included that charge over there. And now because fluorine has again an extra electron, therefore it's going to have a net negative charge. Okay, so this is a very simple example. Now moving on to the next example, this is going to be a bit more challenging and different from the other example that we've just looked at. So again, I'm going to be drawing the individual Bohr model of magnesium. So magnesium has 12 electrons in total, and because it's found in group 2, it will therefore have 2 electrons on its outer shell. So this is what magnesium would look like, and as you can see here, that's one of the valence electrons, that's another valence electron. For chlorine, on the other hand, it's got, I believe, 17 electrons and 7 valence electrons on its outer shell. So this is what chlorine would actually look like if you drew this correctly. Now, we know that magnesium wants to lose 2 electrons in order for it to be stable, and we know that for chlorine, it really only needs to gain 1 extra electron. So therefore, magnesium can lose one of its electrons to chlorine. However, by losing just 1 electron, magnesium is still going to be unhappy because it still has 1 extra electron to give away. As a result of this, you actually need to introduce another electron acceptor to take away the extra electron that magnesium has. So as a result of this, you actually need to add in an extra chlorine atom, and by adding in an extra chlorine atom, magnesium has the ability to give away its other remaining electron for it to become stable. So again, drawing an arrow from the electron donor to the electron acceptor, and now this is happy. So therefore, if I was to draw this mechanism, then this would be my final answer up here, including and showing the movement of the electrons as well as the individual charges. Just to note, magnesium would therefore have a +2 charge because it lost 2 of its electrons, okay? And another way of doing this is that instead of actually just writing both of these chlorine atoms individually, you could just scribble one of these and just go 2 times chlorine, okay? That's just a shortcut way of doing this. I'm now going to be showing you an example of how to do this using the electron dot diagram. So the electron dot diagram is going to be a lot more simpler because you don't have to draw all these unnecessary inner shell electrons. So therefore potassium, we know that it has one valence electron because it's found in group 1. So you can draw potassium like this, and sulfur is found in group 6, so therefore it's got 6 valence electrons. Okay, in this case over here, potassium needs to lose 1 electron for it to be happy, and sulfur needs to gain 2 electrons in order for it to become happy. So in this case over here, potassium can give away 1 of its electrons, and in doing so potassium is now happy. However, sulfur is still unhappy because it's not stable. It's unstable because it still needs 1 extra electron in order for it to become happy, right? So therefore you need to introduce another electron donor. So therefore in this case, because the electron donor is potassium, you're going to be introducing another potassium atom in. By introducing another potassium atom, potassium can therefore give away this electron, and now sulfur will become happy. So in doing so, this is going to be the correct answer, and again, make sure that you include the charges. For the very last example, we're going to be looking at magnesium and oxygen. Magnesium would look something like this because it's found in group 2, whereas oxygen is found in group 6. Magnesium needs to lose 2 electrons, whereas oxygen needs to gain 2 electrons. And because these are a perfect match, therefore you only need to have 1 of each. So therefore, this is going to be the correct answer, and the individual charges of magnesium should be 2+, whereas oxygen should be 2-, okay? So what I want you to do now is I want you to either use the Bohr model or the electron dot diagram to actually draw both of these examples over here. Because I can't really check to see what you're doing through Edpuzzle, what I'd like you to do is I want you to please email me what your drawings are for each of them before you actually finish this video. So if you guys have done this correctly for lithium and oxygen, I'm actually going to be doing this using the Bohr model. Lithium looks like this. Oxygen, on the other hand, looks like this. In this case over here, lithium can give away its electrons over to oxygen, but oxygen is still going to be unhappy. So therefore, you need to introduce another lithium atom so that oxygen can be happy. So therefore, by introducing another one, you can put an arrow here like this. Therefore, this is going to be the answer for part A. For part B, calcium sulfur, calcium is found in group 2, whereas sulfur is found in group 6. So therefore, calcium needs to give away 2 electrons. Sulfur, on the other hand, needs to gain 2 electrons. And because the number of electrons kind of match between these 2 ions over here, therefore you only really need to have 1 of each, and therefore this is going to be the correct answer. So on this particular slide over here, this is just a summary of the different ways of how you could actually draw the electron transfer process. Remember, there's the Bohr model as well as the Lewis dot diagram. If you have the option, always opt for this option over here because this would be less time consuming. The only questions that I'd like you to do in order for you guys to get extra practice are these 4 questions over here. So have a go, try this in your exercise book and email it to me so I can see how well you're doing. This is essentially the end of today's video. This is the end of today's video. Thank you guys for watching. I'll see you guys again in the next video. Peace out. Bye.